Alright everyone, welcome back. My name is Mr. Santos and today's topic is the AVR's status register, or SREG as is called. Many microcontrollers have a particular register designated for recording particular conditions or events when they are detected, and usually these conditions relate to arithmetic operations. For example, if you take two numbers that are exactly the same and you subtract them from each other, you're going to get 0, right? The microcontroller will indicate such a condition by setting its flag, the Z flag, to 1 to tell you that you just had an operation, arithmetic operation, and the result was 0. If you take a number and subtract it from another number and the result is a negative number, then the negative flag is going to be set. Okay, and etc. etc. So we're gonna explain these. We're gonna explain these one by one real quick, and then we are going to talk about, basically understand the difference between carry and overflow. Okay, because this is usually confusing, and it actually was confusing even for me when I started to understand the concept between carry and overflow, and that's really the primary goal here of this video. Then we're going to talk about how to intuitively identify carry and overflow conditions, and also look at how to identify carry and overflow conditions by looking at the binary operation itself. We're going to talk about the differences between how the microcontroller sets the flags when you're doing addition versus what you will see with the flags when you're doing subtraction, okay, to motivate this discussion. So let's just go ahead and get started, and let's start talking about the flags real quick. So here's the status register present in the AVR microcontroller, and you will see that if you use the debugger in the simulator, you can look at the SREG and it'll tell you what the status of each of the bits are. Okay, to the left, starting from left to right, we have the I flag, which is the global interrupt flag. Every device, a microcontroller has many devices. It has a serial port, it has an analog to digital converter, it has a timer, and each of these devices can generate an interrupt. It will interrupt your program to let you know that something in that device happened, and therefore you should look into it. And by looking into it, that really means by executing the interrupts service routine. Okay, and you'll learn that in a different video and in a different laboratory exercise for my students. But basically, there's two things that you need to know. You can actually turn this global interrupt using the SEI instruction, which means set interrupt. You will set it to 1, and the CLI instruction, clear the interrupt, will clear this to 0. So whenever you have devices and you expect to make use of those devices' interrupt capabilities, the device, you could turn the interrupt for the individual device, but the interrupt will not be serviced until you turn on the master global interrupt of all interrupts. Okay, it doesn't matter whether you have devices with interrupts enabled. If you don't have the global interrupt flag set, nothing's going to happen. Okay, so just remember that. The T stands for bit copy storage bit, and this is a flag that is for you to use however you want to use it. Okay, the instructions for, let me put that in here. The instruction for the bit copy storage is the bit clear. So I think it's a clear T. No, sorry, CLT to clear the T flag, and SET to set it. Okay, you can set that and clear it to your heart's content, to however you want to do. There's some other instructions, like for example, you can actually have a register. Remember, you have 8 bits, so you got bit 0 and bit 7. Let's call this RN, could be any register. You can actually use an instruction to determine, you can actually load any of these bits and load it into the bit copy storage flag, and you can actually retrieve it and put it in another one by using the BLT bit set, the set and BLD to load. Alright, so you could go ahead and look at the instruction set reference manual if you want to find out the details on how to use that. Okay, the half carry flag, that means that whenever there is a carry or a borrow from bit position 3, starting from 0, to bit position 4 and vice versa, then the half carry flag is going to be set. That's typically useful when we're talking about binary coded decimal encoding. In binary coded decimal, you basically divide a byte into 4 halves. So you have 4 bits here and 4 bits here. And whenever there's a borrow or a carry from this bit position to that position, so this is bit position 3, this is bit position 4, right? The half carry is going to get set. So BCD numbers, binary coded decimal numbers, is usually the context by which this guy may or may not be important to you. Okay, let me skip the sign flag for a minute and let's move on to the easy ones. I want to tackle the easy ones first. Zero flag should be obvious. Whenever you have an arithmetic operation whose result is 0, then the 0 flag will be set to 1. Okay, the negative flag indicates the most significant bit. Okay, so that means that whenever you add two numbers or subtract two numbers, it doesn't matter what's happening. Whenever bit 7 is set to 1, whatever this bit is, it will be reflected in the N flag. So if this is 1, then N will be 1. If this is 0, then N will be 0, and vice versa. So again, this will be a copy of whatever happened in the previous arithmetic instruction for the most significant bit. Okay, it's called the negative flag because if we interpret this number as a negative number, that's the key word. If we interpret this number as a negative as a sign number, then that means that the most significant bit represents our sign. And when this is set to 1, that means that this is negative something. What is that something? That depends on what's here. Okay, so that's what the negative flag means. All right, now let's look at carry and overflow. Carry flag is for unsigned arithmetic, unsigned interpretation. Okay, whenever you have a number and you add two numbers and you have, this is bit 0 and this is bit 7, and in between, whenever you have an addition that causes this bit to generate a carry out of the most significant bit, okay, then the carry gets set to 1. All right, so basically this is for unsigned arithmetic. Okay, lastly, there's the overflow flag. The overflow flag only matters when you're interpreting, again, keyword, interpreting a number, a result, as a signed number. Okay, so that means that the number was too big to represent a sign interpretation. Usually that happens when bit 6 either overflows into the next column or there is a borrow from here to here. Okay, because this number is the sign number. When we do sign interpretation, this is our sign number, and the most significant bit is used as the sign. So whenever these numbers overflow, okay, that means we have a carry from bit 6 to 7, not a carry from 7 to the carry flag, from bit 6 to 7, then we have an overflow. Alright, and that's how the overflow gets set. Lastly, there's the sign flag, which is actually unique to the AVR microcontroller, and it's called the true sign. Okay, to determine S, all you have to do is look at the N flag and the V flag and do the exclusive OR of those two. Whatever these two flags are doing will determine what the S flag is going to be. Okay. Alright, now let's go ahead and talk about, give an intuitive interpretation of the overflow and carry. Whenever we are talking about arithmetic operations in computer systems with finite precision, okay, we need to talk about what the precision is. Okay, basically this means the number of bits. Of course, with the AVR microcontroller, we're always using 8-bit arithmetic. Okay, when you have 8 bits, whatever values you can represent depends on whether you're using the unsigned interpretation, okay, versus signed interpretation. Okay, I keep using that word interpretation, and it's really important because to the microcontroller, whatever it has stored in its registers is just a bunch of ones and zeros. The microcontroller doesn't know about sign or unsigned. They're just ones and zeros. How you interpret that number is up to you based on which instructions you choose to use, because some instructions make a signed interpretation of the data and some instructions make an unsigned interpretation of the data. A microcontroller doesn't care what's in there. There's just ones and zeros. Okay, so for example, if we're talking about 8-bit numbers, any register can store a number between 0 to plus 255, right? That's the unsigned interpretation. In such an interpretation, all bits matter. Okay, so we got bit 0, 1, 2, 3, 4, 5, 6, 7. Even bit 7 matters. They're all used to represent, all of them are used to represent the number in question, a positive number. Okay, but you can look at the same value in the same register and you can assume that it's a signed interpretation. In that interpretation, now you're looking at bit 7 to serve as the sign bit in 2's complement, and then here we have the signed number, right? And in this case, then we can represent any number between 0 and plus 127, or between -1 and -128. You always have one more than whatever you can. So if you have n bits, then you can represent up to 2 to the n -1 in the positive scale and -2 to the n on the negative value. Okay, so that's this and that. Okay, the same if we had 4 bits. So suppose we have 4-bit arithmetic, just because this always works. You have 4-bit arithmetics, then you have any value. If you're using positive interpretation, then you can represent a value between 0 and 15. Okay, positive 15. And if you have the unsigned interpretation using 4-bit precision, that means we represent 0 to positive 7 and -1 to -8. Okay, 2 to the 4 is 2 to the 4 minus 1. 2 to the 4 is 8, -1 is 7, and 2 to the 4 is 8, and add a negative and you get -8. Okay, so that's the interpretation. The microcontroller doesn't care, right? To prove this even further, let me show you how the AVR does some basic arithmetic and subtraction and compare that to the way that we do arithmetic. So let's just go ahead and do an example. Suppose you want to add 2 numbers on a piece of paper, the way normal humans do. So suppose we want to take 5 subtract 7. The answer obviously in your head is going to be -2. Now let's suppose you're writing a program in the AVR to perform this arithmetic. Okay, there's 2 possible ways this can unravel. Okay, you can choose to write the following program: LDI R16 5, LDI R17 -7, and then you use the add instruction to add R16 and R17. The interpretation of this code is that you're storing 5, you're storing -7, then we want to add these 2, and the answer we expect obviously should be -2, period. Okay, or we could do this. We could load R16 with 5, we could load R17 with +7. Notice that here we use -7. Okay, and then I can invoke the subtraction instruction, R16 R17. This interpretation now is saying you load 5 in a register, you load +7 in another register, and then you call the subtract operation. I expect the same answer is going to be -2. Okay, and the microcontroller is going to give us this. But the question is, how is the microcontroller, and in particular, how are the flags affected? Okay, so let's illustrate. All right. again, we assume 8-bit arithmetic. So suppose we have in R16 this value. 5 in hex is 0, 0, 0, 0, 0, 1, 0, 1. And then R17 we loaded minus 7, but we need to find minus 7 in 2's complement form. Okay, so let's just kind of do it in this corner over here. I'm going to show you the shortcut. Okay, 2's complement shortcut, we write the positive number of 7, which is 0, 0, 0, 0, 0, 1, 1, 1. To find the 2's complement, the negative representation of this number, okay, all you have to do is scan from right to left. When you find the first 1, not the first bit, the first 1, copy it as is, and then change all the other bits that follow. So we have 0, 0, 1, 1, 1, 1, 1. Okay, so minus 7 will be represented in a register as 1, 1, 1, 1, 1, 0, 0, 1. And that makes sense because this tells me that this is negative something, negative 7. Alright, and then it says that we're going to use the add instruction. So we're going to use basic addition here and add these two numbers together. Okay, so we have 1 plus 1 is 0, 0 plus 0 is 0. I made a mistake. Let's try again. 1 plus 1 is 0 with a carry. Okay, 0 plus 0 is 0 plus a carry is 1. 1 plus 0 is 1, 0 plus 1 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 is 1. Okay, what is the answer? This is negative something. If I assume a sign interpretation, negative something. So to find what the answer is, again we use the trick. We scan from, and that means that the register R16 is going to show FE. Okay, to find what this negative something is, so we have negative something. We use the trick again. We scan from right to left. And when we encounter the first 1, we leave it as is and flip everything else. 0, 0, 0, 0, 0, 0. That's this guy here. Okay, what does that translate to? 0, 2, which is correct. Negative 2. So we got the right answer. But do we have the same flags? Let's see. There was no carry. First of all, it's not 0. So the Z flag is going to be 0. Okay. There was no carry from bit 3 to bit 4, so that means that the half carry is 0. There was no carry between the most significant bit into the carry flag, so the carry flag is 0. So we got half carry 0, carry flag is 0. Did we overflow? No, because these are opposite signs, and this is perfectly legal. We did not go over our arithmetic that would create an overflow. So therefore the overflow flag is 0. What about the negative sign? Remember, the negative flag is a mirror image of what the most significant bit is. Well, since it's 1 here, that means n is 1. Okay. Lastly, the sign flag. Remember, the sign flag is the exclusive OR of whatever the n flag is and the overflow flag. So 1 and 0 exclusive OR is 1. That makes sense. That means that our result is negative and its true sign is set. So this is the answer that you would see if you did this code on the simulator and try to do this way. Now let's look at this one. So once again, we're loading now positive 5 and positive 7. So R16 is going to be 0, 0, 0, 0, 0, 1, 0, 1, and R17 is going to be 0, 0, 0, 0, 0, 1, 1, 1. And now we're using the subtract instruction, so we're going to subtract these two numbers. Okay, subtraction has to be done the same way that we humans do subtraction. When we subtract two numbers, so long as we don't have to borrow, we just subtract the big number from the little number and provide the answer. If the top number is smaller than the bottom number, then we have to borrow from the adjacent column. and then when we borrow a 1, it turns the primary column a 10, or it adds a 10 to it. But here we're working in binary. When we steal a number from the adjacent column here, then it becomes 2 because we only have the numbers 0 and 1. Okay, so let's just proceed. 1 minus 1 is 0. 0 minus 1 is not possible, so I have to borrow from this guy and steal a 1. It becomes 0 here, and this becomes 1, 0. Remember, this is not 10. This is 2, the number 2 in binary. 2 minus 1 is 1. Then I get here, 0 minus 1 is not possible, so I have to borrow from the other column. But it's a 0, so I cannot borrow. So then I borrow from this column, but it's a 0, I cannot borrow. So try this column, no. Try this column, no. Try this column, no. Everybody's broke. Therefore, I have to borrow from where? From the bank. And that is the carry flag, right? So this automatically becomes 1. And therefore, a 1 is borrowed to this guy, and it becomes 1, 0. But then this guy needs to borrow from here, so I steal a 1, and this becomes 1, and this becomes 10. But this guy needs to borrow a 1 from this guy, so I steal a 1, this becomes 1, this becomes 2. I said 10, I said 2, or 1, 0. Then, but this guy needs to borrow a 1, so I steal a 1, this becomes 2, alright, and this guy becomes 1, etc., etc. But this guy needs a 1, so this becomes 1, and this guy becomes 2. But then we come down to where the reason this whole process started. This guy needs a 1, so I steal a 1, it becomes 1, and this guy becomes 2. 2 minus 1 is 1. Okay, 1 minus 0 is 1. 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 What is the answer? Still FE. The same answer. Okay, so under the sign interpretation, this tells me I have a negative something. What is that negative? Well, we already did it here. You change it over and you get minus 2. So everything matches, but do we get the same flags, or did we get the same flags? Okay, going back, the answer was not 0, so Z equals 0. Okay, there was a borrow from bit 4 into bit 3. You just saw that. Therefore, the half carry is set to 1. So H equals 1. There was a borrow from the carry flag to borrow along all these bits here. Therefore, the carry flag is 1. There is no overflow because I did not push the arithmetic beyond the bounds that I'm allowed in, in the register under signed interpretation, so the overflow is 0. The negative flag, it's a mirror image of the most significant bit, so therefore it has to be 1. Lastly, the sign flag equals the exclusive OR of whatever the end flag is doing and the overflow flag is doing. So 0 plus 1 is 1. And that makes sense. This is a negative number, so its true sign should be negative, and that's reflected in there. Alright, so that is how you would show how to do this arithmetic by hand. Now let's talk about how to identify the overflow. I talked about intuitively by overflow. Okay, let's talk intuitively first, and then we'll come back to this. Intuitively, okay, if I have, again, we're talking about 8-bit arithmetic. This is important. Precision, you always have to ask the person, well, what is the precision? Okay, the precision is 8 bits here. Intuitively, if I have, well, you saw in the previous answer, what was the answer for our arithmetic? It's FE. Okay, that's just FE. It's just a bunch of binary numbers. But you saw that this number has 2 interpretations. Okay, so FE was 1111 1110. Okay, so this number FE, is that number minus 2? So let's go back. Was this number minus 2, or is it 254? That's up to you, right? yeah, you typed it on your code as -7, but again, I'm repeating this again. The microcontroller doesn't care. The microcontroller just sees FE. Whether you interpret this number as -2, okay, so that has two interpretations. That number can be -2 if you choose to treat this interpretation as a signed number, but if you choose not to treat it as a signed number in your mind, then this number is just 254. So FE is simultaneously plus 254 or -2. But that depends on how you interpret it. Okay? And by interpreting, that means by the types of instructions that you use. Okay? Certain instructions are signed and certain instructions are unsigned. Okay? If I remember from memory, there's two instructions on branching. For example, you have the branch if less than, right? If you're comparing two numbers and you have a number like this in the register, you know, a branch if less than, and then you have a branch if lower. This instruction will look at this value and interpret it, I believe, as a signed number. So in this case, it will treat it as a signed number. And this instruction will do the same operation, but it will treat the number as an unsigned number. So that's up to you how you choose to treat the number. The microcontroller doesn't care. Okay. Interpretation very quickly of the overflow flag. So again, I want to make sure that you're clear about this. Let's talk simply. Let's go back to 4-bit precision. Again, you always have to ask the person, well, what is the precision? 4 bits. Okay. So 4 bits for unsigned arithmetic gives me a number line between 0 and 15. Okay. So if I happen to have a number here, 14, and I add 1 to it, then I get 15. But if I have 15 and I add 1 to it, then this recycles back to 0 because we're going to overflow. The true number is supposed to be 16, but we cannot represent this number with 4-bit arithmetic, right? This is not possible, and this is where the carry flag gets set to 1. If you have sign interpretation, right, now we have a different interpretation. You have 0, you have +7, and you have -8. So if I have a number here +6, so you have +6 and you add 1, you get +7, which puts you here. We're perfectly fine. If I take +7 and I add 1 to it, now I get supposed to be +8. It'll put you right here, but that's not possible because this is illegal territory. Right? It is not possible to represent +8 in sign interpretation. In sign, if we do sign interpretation. So this is going to make the overflow flag be set to 1, but not the carry. Same here. If I have -5, so you have -5, and you subtract. Now if we subtract numbers, we're going to get pushed further down into the barrier here. So if I add -2, then the answer is -7, which puts us right there. No problem. The overflow flag is 0. Everything's good, right? And if I add 1 to -7, and I get -8, that puts me right here. No problem. The overflow flag is 0. But then if I take -8 and I add another number, then I get -9. -8, -1, -9. I cannot represent -9 as sign interpretation. Okay, so therefore the overflow flag is set. Alright, so intuitively, overflow occurs when you add two numbers of the same sign. So if you take a positive number and added another positive number, then what's going to happen is you could potentially be pushed further to the right, and you may potentially break the barrier. And if you have a negative number and you add to it another negative number, then you get pushed in this direction towards the negative barrier. If you go past that barrier, then you have an overflow. Okay, and that's just how you think intuitively. So therefore, you will never have a problem if you're adding a positive and a negative number. Period. It's just never going to happen, right? This is why I was confident here when I told you, well, we don't have overflow because we have opposite signs here for sure, right? And here I have the same signs, but I'm doing a subtraction, which will treat the other number as an opposite sign. So therefore, I don't have an overflow either. I'm confident of that. So that's the difference between carry and overflow. Now, just because you have an overflow condition does not mean something went wrong. Again, if the interpretation is supposed to be a positive number, then you don't care that you have an overflow because you're not even interpreting the number as a negative number. The microcontroller is just letting you know, hey, if it so happens that you're treating this number as a sign number, guess what? We have a problem. You have an overflow. But if you're not interpreting the number as a sign number, then you just ignore the overflow. You don't care about it, right? So this is the difference between carry and overflow. All right, so please remember that. Please remember that there are many instructions that you can use to, you usually don't write to the SREG directly. There are actually special instructions that are provided to set the individual flags. I think the half carry flag has a set SEH to set the half carry and CLH to clear the carry flag. I think there's probably a CLC and an SEC instruction to clear the carry and set the carry, etc., etc. You can look at, and I cannot stop recommending enough that you look at the instruction set. There's so many instructions that allow you to control, manipulate the status register. Okay, so here I'm looking at the clear negative flag. All right, and there's also instructions, conditional instructions that you can use. Like you can branch if the T flag is clear. You can branch if the T flag is set. You can branch if the overflow flag is clear. You can branch if the overflow flag is clear. You can branch if the carry is set. Or you can branch if not the carry set. I believe. Yeah, branch if carry clear. Branch if carry set. Again, you always have to come back and just look at all these instructions so that you can build a mental toolbox of what instructions you have at your disposal to do work, to write your program in assembly. You're not going to know what to do if you don't even know what you have available. So always make sure you just look at these and every once in a while and just remind you so that when you have a problem you can remember and say, oh yeah, I remember seeing something in the instruction set manual. Then you can go in and then you can find out. Okay, last thing before I finish here. Some instructions affect flags and some instructions do not affect flags, and some instructions affect only a few flags. So for example, the add instruction, when you go to the instruction set manual, you look at the flags and it tells you what flags are affected by this instruction. So the add will potentially change the half carry, the sign, the overflow, the negative, the zero, and the carry. That's what this double arrow means. It might be changed from 0 to 1 or 1 to 0. We don't know. All we know is that this instruction can potentially change all these flags, and it will leave the global interrupt and the bits copy storage flag alone. That's what the dash means. Then there's some other instructions such as the call instruction. The call instruction does not affect any of the flags because it has nothing to do with arithmetic, so it's not going to generate any conditional events there. If we look at some interesting instructions like the COM for the ones complement, the ones complement will leave the IT and half carry flag unchanged. It may potentially change the sign bit and the negative and the zero flag, and it will for sure set the overflow flag to 0, and it will for sure set the carry flag to 1 anytime you use this instruction. Okay, so these are things to keep in mind. You may have a program that depends on the value that was previously set in a flag by a previous instruction, but then you may have another intervening instruction that can change it and you may lose that information. So just keep that in mind, that instructions can change the state of the flags. Actually, before we leave here, I'm very sorry again. I forgot to talk about I talked about overflow and carry intuitively, but how do you identify by actually looking at the bits in the arithmetic? Well, the rule is simple. Of course, you could determine a carry by just looking at the most significant bit. Do you actually carry out into the carry, or do you borrow from that? That's how you determine the carry. But how do you determine whether you have an overflow condition by looking at the arithmetic? It's actually simple. Overflow occurs whenever there is a borrow from bit 7 to bit 6, in this case, in the case of 8-bit arithmetic, okay, or carry from bit 6 to bit 7, but there is no carry out. So if you have this but not that, you have an overflow. And if you have this but not that, you have an overflow. If you have both a carry from here to here and a borrow from here to here, then there is no overflow. And if you have a carry from here to here and also here to here, there is no overflow. Okay, so look at what is happening always between bits 6 and 7 and the carry. Okay, so if you have this, a 1 needs to be carried over to here, but here is 0, then you have overflow. Okay, similarly, if you have a borrow from here, okay, but you have a 0 here, then overflow is 1. Alright? But if you have the opposite situation where you carry a 1 from bit 6 to 7, and you carry a 1 from 7 to the carry flag, or you borrow a 1 from the carry flag to bit 7, and you also borrow a carry from 7 to 6, okay, they're the same, so therefore overflow will be 0, overflow will be 0. And going back to our example, we have no carry when we're doing addition. There was no carry from 6 to 7 and no carry from 7 to the carry flag. Same when we did the subtraction. When we did borrow, we borrow from the carry flag to bit 7, and then there was a borrow from bit 7 to bit 6, 1 1. So therefore overflow in both cases was 0 and 0. Okay, alright, so remember those rules, and now I promise I am done. Thank you.